All right, MiniExam 6 demo. So this one is focused primarily on regression hypothesis testing type questions. So we're just going to walk through this. This is very similar to what you can expect on MiniExam 6. So this first question is asking about a researcher using a data set with some information about the sample mean and the sample standard error. And so we're just going to go through and try to interpret some of these questions. Which of the following correctly describes the sampling distribution of the mean difference under the null hypothesis of no effect? Okay, so what we're told here is the mean difference, so the difference between treatment and control, has a value of 450, and then we're given also the standard error. So what we know about the distribution of the differences in sample means and the distribution of sample means themselves is that it's under the null hypothesis is going to follow a t-distribution centered on the null hypothesis. So here, the null hypothesis is that there's no effect. So that's, first off, I mean, it's not going to be a normal distribution. We know it will be approximately normal if the sample size is large enough. But it's not going to be exactly normal. And then it's the sampling distribution of the mean difference under the null hypothesis is going to be centered on the null. We talk about, how it's mathematically equivalent to center the sampling distribution on the sample mean for purposes of constructing p-values. But the distribution itself is not centered on the mean. So this is just going to be straightforwardly the last one. Okay, so t-distribution centered on the null. Okay, so the p-value for this test is given to us by this number. Which statement most accurately explains what this p-value means? So when we think about a p-value, what we're saying is that we're talking about, under the sampling distribution, the t-distribution, that we end up observing some sample mean as extreme as the one that we do under the null hypothesis with a p-value. So this first one isn't, exactly correct. Which statement most accurately explains what this p-value means? So there's, this, we can think about, a distribution around. So we talk about so we have our x bar, and we think about, how far away 0 is from our x bar. But we also need this equally extreme value on this side. So the p-value is representing the area under both of these tails. And so a p-value, if this is pretty close to being correct, but first off, we need to think about not just the 0, so the probability of getting something that's equal to 0, but also what the p-value is doing is capturing the areas sort of more extreme than 0. So it's not just 0, but also everything else that's kind of more extreme. But then we also need the area on the other tail. So we will essentially only do two-tail tests. And so this is almost correct, but we also need to not just think about 0, but also think about all of the things that are more extreme than 0 and extreme on the other side. So even though we can center the t-distribution on x bar, that doesn't mean this is the correct one. Okay, so there's a 2.8% chance that the sample mean difference is 450. So again, this is not exactly correct, sort of in the same ways that this one isn't correct. we're not just thinking about 450, we're thinking about a lot of other possibilities as well. So we have to think about sort of the extremeness of our events. Okay, so this third one, if the job training program truly had no effect, so we're sort of assuming the null here, we'd observe a difference of 450 or more extreme 2% of the time. So I'm going to hold on to this one as a possibly correct answer. We're saying under the null, we're drawing a bunch of samples. How extreme are they? Well, they're this extreme 2.8% of the time. So that seems consistent with me. Well, maybe it is consistent with me. It's definitely seems consistent to me. Okay, and then the probability that our conclusion is wrong 2.8% of the time. Well, what conclusion? I'm not sure. So this one, we'll roll it out. Okay, so we have one remaining, which is consistent with what a p-value is doing. So I'm going to select that one. Nice. So question 2 is about a simple linear regression model. So we have y is equal to beta 0 plus beta 1 times x plus our error term. And we're given some coefficient estimates here. So this is beta 1 is equal to 0.25. And then we have a standard error on beta 1 that's equal to 0.25. Okay, so first we're going to interpret the coefficient. So let's just run through these. For every increase in y, x increases by 0.25 units on average. So this one is not right. So we have, our beta 0, and then we have our slope here. So every time we go up by 1, so this is an increase of 1, then y goes up by beta 1. So this is our 1 and our beta 1. So beta 1. So nice. So this is sort of our model. So this is not right. We're not saying x is increasing by this number. We're actually saying y is increasing. And that actually turns out to be the option right below. So for every 1 unit increase in x, y increases by 0.25. Nope, I can't speak apparently. Cut. Just kidding. We're doing this live. So we're increasing y by 0.75 units on average. So this one seems to be possible, but I'm going to hold on to it for a second. So then when y is equal to 0, so when we're here, y equals 0.75 on average. So this isn't right. The answer here would be the interpretation for the intercept. So that would be for beta 0. Okay, and then the last one is 75% of the variation in y is explained by x. So no, beta 1 is not talking about the percentage of variation explained by x. It's just capturing the slope. Okay, so this is not right either. This isn't right, so that means this one must be right. This one's consistent. Okay, so then B, to test whether there's a statistically significant relationship between x and y, we test which one of these tests. So here, the question we're after is whether there's actually a slope. And so this first one is not right because it's looking at the intercept. The second one could be right, so we're going to hold on to that. We're checking whether the slope is actually different from 0. And then this third one, we're checking whether the slope is exactly this number. And this isn't exactly what we would want to test if there's a relationship, because this is like a specific relationship, and that's not usually what we're trying to test. And then the last thing is y is equal to 0 versus y is not equal to 0. Well, the vertical axis here doesn't really matter for the question at hand. We're thinking about the actual slope. So again, this one is not correct. So we're just left with this null hypothesis. Okay, so the third question, the null distribution for testing the above hypothesis follows what? And so this one actually we're going to talk about this in some detail. We know, first off, that it's not following a normal distribution. It's going to be pretty close if the sample size is large enough. But what we do know is that it follows a t-distribution. And t-distributions, as we've talked about so many times, are very similar to normal distributions, but have a little bit of extra variability built in because of the fact that we're using the sample standard error. Okay, so we have the t-distribution with mean 0 and standard error of 0.25. So here what we're saying is we're centering the t-distribution on 0. And then for this one, we're centering the t-distribution on 0.75. Okay, so these are two possibilities given to us here. And we should be specific about what this question is asking. The null distribution for testing the above hypothesis follows what? So if I were to write a solution guide for this, which I've done, I would actually count both of these as correct. This first one is the technically correct answer. What we do is we center the t-distribution on the mean, on the null hypothesis, which is 0 in this case. So we're testing whether the coefficient, or we're testing this one, whether the coefficient is 0. And so we center the distribution on 0. But like we've talked about so many times, it's mathematically equivalent when we're calculating p-values to center the t-distribution on the sample mean and then check for the area in the tails more extreme than 0. But the distribution itself is this one. Okay, so here I would give at least lots of partial credit for getting this this possibility, but this one is the truly correct answer. Okay, so no one can read what that says. That says partial, like partial credit. And I would probably give almost all points for this one too. Okay, so this last question, a researcher conducted a study on climate action running a regression model predicting a city's carbon emission reduction based on renewable energy investment with the following results. So our Y variable is predicting carbon reduction emissions, carbon emissions reduction, and then we're predicting it using renewable energy investment. So, on the horizontal axis, we're trying to predict, so we have our X variable, which is investment. And then on the vertical axis, we have reduction. Okay, so cool. We're trying to reduce carbon emissions by investing in the technologies that make that possible. All right. And then so we're given a bunch of results here. This is like our standard regression output. And then we're asked to interpret some of this. So the first question, the most accurate interpretation for the intercept coefficient is what? So let's just draw a little model here. So this thing is our beta 0. And we're asked about interpreting beta 0. So the average reduction, so when we're doing this, actually let me do this in a different color. So our intercept, we're going to look at a couple of things. We might even look at the confidence interval. Well, we'll look at it for the coefficient, investment coefficient later. So here, the most accurate interpretation is what? The average emission reduction across all cities is this. Well, this would be true. So we would use the intercept as the average if we didn't have a slope. But because we have a slope, then that sort of turns the intercept into a number that doesn't necessarily represent the mean. It can, but it's unlikely to. It doesn't necessarily represent the mean. So the second is when renewable investment is 0, the predicted emission reduction is what? Or is this number. So this looks fine to me. So we'll hold on to this. The emission reduction increases by this much for every $1 million invested. So this looks like an interpretation of beta 1, so the investment. So that's not going to work. And then this last one, this is talking about the variation explained. So this is also not going to be correct. So the second one will be our interpretation. When renewable investment is 0, the predicted emission reduction is this amount. Okay, so nice. So that's for the intercept. The second question is 95% confidence interval for the investment coefficient tells us what? So that's going to be this here. We are 95% confident that renewable investment has a statistically significant effect on carbon reduction or emission reduction. Well, so with this question, I mean, there's some truth to what this question is, or this option is saying. But we're not saying, we're not really doing enough work to be able to talk about statistical significance here. If we were to compare it to 0, then we would see that 0 is not contained on this 95% confidence interval. But this statement alone is not quite enough. So for the second one, if we took many samples, 95% of the calculated confidence intervals would contain the true investment coefficient. So this is like we're running a bunch of samples, like we've done with our simulations in class. We construct the confidence interval, which moves around every time we run it because we're getting a different sample, and then our 95% confidence interval is centered on the sample mean, or in this case, the slope. And then we get our 95% confidence interval from the t-distribution. So here, this is very consistent with how we actually construct these things. So I'm going to hold on to this. 95% of cities would have an investment effect between these two numbers. Well, so again, when we're running the interpretation of a 95% confidence interval is not saying that this is the true confidence interval, that we're confident with this range. What it's saying is that upon repeated samples, the truth will be on this interval, whatever, like each of those intervals, 95% of the time. So we are actually not confident in this. And then the true investment coefficient is between these two numbers, and with a 95% probability. So again, what we're saying with the 95% confidence interval is that when we run this a bunch of times, and construct a confidence interval in the way that we're doing, 95% of the time the truth will be contained on this interval. But it's not saying anything specific about these numbers. So this isn't correct either. So this one would be the correct answer. Okay, so the last question, which statement about the regression results is correct? Both the intercept and the investment have statistically significant effects at this level. Well, this is true. We have a p-value less than 0.05 and an investment effect that's also significant at that level. But let's check the others too. So the effect of the intercept is exactly this much larger than the effect of the investment. Well, we don't know exactly. So these are our estimates for the effects, but we don't know that it's exactly equal to this. This is like our best guess. If we were to say our best guess is exactly this much larger, then we could plug this into a calculator and check if that number is equal to this. But we don't even have to do that much work because we know that we can't say anything exactly. We're just saying our best guess. And here this doesn't allow for sort of any nuance in the interpretation. Okay, so the p-value on investment indicates there's a 1% chance that renewable investment increases emission reduction. So here this 1% chance is referencing this p-value here. And let me just check I'm doing this right. The p-value on investment indicates, so this is saying there's like a very small chance that that there's an effect here. And the interpretation here is actually flipped. So this is also wrong. We're very confident that it does have an effect. And then this last one, we've proven that renewable investment causes emission reduction. Well, this is just, this is like classic incorrect. We haven't proven anything here. We're just very confident that there is an effect, but no proof. This is just, an estimate, but there's the possibility of being wrong still. So we haven't proven anything at all. Okay, so the answer here is this first one. So you can see there's a lot going on with this type of question, or this type of mini exam, like lots of very similar types of questions. This is very similar to what you can expect on MiniExam 6, and hopefully this was helpful. I'll see you in the next one.